Hello all, and welcome to the ISTRC Gustav Eiffel University webinar, an overview of Gustav Eiffel University research initiatives and actions about cooperative and connected automated mobility. Among the audience, we have researchers from the academy, industry, and public sector in Israel. We just want to let you know that we are recording the webinar and we will upload it to our website and publish it during the next month, probably. The second half of the webinar will be dedicated to questions and answers. So please use the Q&A button to submit your question during the presentation. We will answer it during the second part of the webinar. Now, this webinar goal is to get familiar with the Gustav Eiffel University and its initiatives in smart transportation domain, while explore areas for collaboration. And the plan for today is to have a brief introduction of the Gustav Eiffel University, and then an overview of the university research initiatives and actions about cooperative and connected automated mobility. And then potential areas for collaboration. And then we'll have the Q&A part. So I'm happy to invite Dr. Dominique Gruyer, Researcher Director HDR, and PICS-L Laboratory on Perception, Interactions, Behaviors, and Simulation of the Road and Street Users, Head of the International Associated Laboratory ICCAM, France, Australia, Deputy Director of the COSYS Department of Autonomous and Connected Vehicle, FSTTAR Program Coordinator for Autonomous and Connected Vehicle. And also Dr. Sio-Song, TPE Researcher at University Gustav Eiffel. So Dominique, the stage is yours.
Thanks a lot for this nice introduction. So now I will share my slides. Is it okay? Do you see my first slide?
Yes.
Okay. So today I propose to present an overview of UGE researches focus on cooperative and collaborative automated mobility, because we are working strongly on this aspect, how to develop a new mobility means, and especially automated mobility with shuttle, with individual cars, and with level 3 and 4 of automation, and also share mobility with automated functionalities like robot taxi or such a type of transportation means. But before to provide you the summary, an overview of our researches in UGE, first I would like to present you UGE. What is UGE? So it is a very new university starting from 2020 with the merging of a lot of different organisms. So first one is ISTRC. ISTRC was the French research institute dedicated on transportation. Transportation with a very large scale, not only road transportation, it is also with a train, with a boat, with all types of transportation means. And not only on the technological aspect, but with a societal aspect, human factor, and it is a very large scale. Second one is University Paris East Marne-la-Vallée. Then after ICCAM Paris, it is a famous engineer school in France, and also engineer school about Paris city is the engineer school dedicated on architecture, in fact. And we have also ISTRC. It is a specific school about geographic domain. And inside, for instance, it is how to develop a new generation of map, HD map, and management of GPS data, and all these aspects. And the last one is about also architecture. So now we have a huge university, not only focus on a specific region. We have a lot of campus all around France. So the main one, headquarter is in Marne-la-Vallée, but we have also another campus in Versailles-Satory with a huge facility means. We have another one in Lille, we have in Nantes, in Belfort, Lyon, Grenoble, Salon-de-Provence, Marseille, and Bordeaux. So in this university, we focus our effort on three main challenges. So first one is about the resource efficiency with the design, management, and development of new urban spaces and objects. The second one is more about a safe and resilient city with urban risk. And the third one is about a smart and connected city. And so about the smart and connected, it is also development of the different technologies and the ecosystem and the social aspects. We have five main scientific fields covered by researchers and teacher researchers, because it is an university. So we have a lot of students also. We have 23 research components, and it is really new for a university, for French university. We have a specific vice presidency dedicated to the assistance to public policies. So we have a strong link with ministries. And we have an extended international network with a lot of countries in Europe, but also with China, with Australia, with Canada, with North Africa, South Africa, and a lot of parts around the world. About the teaching part, we have at this moment, it is the current state of the university. We have only 17,000 students. So it's not yet a lot. It's not a huge university in terms of students, but in a short term, we expect to reach at least 30,000 students. And among these students, we have students of in master, undergraduate level degree, and we have also a lot of engineer. So we have 4,000 engineering students, and we have also, it is interesting, around 500 PhD students. About the staff, we have 2,300 civil servants in this university with 200 teachers, 400 teacher researchers, and a bit more than 500 researchers. And then after a huge administrative and technical staff. The ranking of this university in terms of research focused on transportation in the Shanghai ranking, we are the first French university. And also about teaching, we are the first French university in terms of apprenticeship status. We have a lot of apprentices in UGE. So I said we have a lot of campus and 5 main one. So the 5 main one are Marne-la-Vallée, Lille, Nantes, Lyon, and Salon-Provence, Marseille. And after it is a small one. So now, more about our researches in order to understand why we develop the different topics, subdomain of researches. It is important to have in mind this overview of the road context and the road environment. In fact, the road environment is a set of humans, users, who use, interact, cooperate with a set of technologies and mobility means on dedicated and adapted infrastructure to move efficiently and optimally according to a set of criteria. So we have mainly 4 criteria with safety, energy and pollution, mobility, comfort, and health, and 4 personal and economic goals. So it is a nice definition of the road ecosystem. And from this definition, we can highlight 4 main domain and key components also. So first one is driver and road users. And so we have interaction with the ego vehicle, some technologies, some systems, and the other vehicle, the other dynamic system objects. And so the driver using the ego vehicle will drive on a specific infrastructure and on roads. So we have infrastructure in order to use specific services, mobility services, and with some also requirements and constraints about the efficiency of traffic. So we have a loop, and we in center the different issues and criteria we have to take into account in our application. So there it is a very micro modeling of the road network and the road environment. Then if we extend this with a great set of humans and a great set of vehicles in use traffic, meets traffic, with a lot of different configuration for our infrastructure. So we will have agglomeration, cities, territory. And then we have a hat with a society, and we have also the definition and the proposal of some recommendation, but also a standard in order to have an efficient system. So from the micro point of view and about the ego vehicle technology system and infrastructure, we have in fact a set of key components, and it is important to assess the current state of this key component in order to develop a specific services of mobility. So first one is obstacle. So we have to detect and to identify the different objects surrounding the ego vehicle and a human. Then we have the road with configuration of a road. So with the road surface, the free navigable space with the type of road marking, with the number of lanes. Then we have the ego vehicle with the current state of the ego vehicle and the capabilities of the ego vehicle and the current positioning also in this environment. Then we have the environment more focused on what is the current state of the weather of the roadside and the type of building and the type of infrastructure. And then we have the last and not the least key component is the human and the driver. And there it is necessary to develop some specific application in order to have an efficient monitoring of the driver and in order to have a prediction, anticipation of the state of the driver. And it is very important to have this estimation of the current state of the driver in order to have the capability to give back the control of a vehicle with a very low level of risk. So when an automated vehicle assess a very risky situation and the system is not able to handle and to manage the current risky situation, so the system will send a request to intervene to the driver, and the driver will have to perceive the environment and to have the appropriate reaction with minimization of the risk. So it's not so easy to implement and to reach such a goal. So we have also to keep in mind when the driving situation is a complex situation with a lot of different level and possible states. So we have first one is a normal driving. Then we can enter in a space with high level of risk, it is a danger phase. And then if we continue, we will enter in a very risky environment with a possible accident, but with the capability to avoid a crash. And then it is the subspace with an available accident situation. And so there we have the critical point with the collision, and then after we have to implement a lot of different mechanisms in order to mitigate the severity of a crash and to also switch on some messages, to send some messages and to start some process in order to send some assistance and help to the different human and driver involved in a crash. And if we extend, we can see it is not only risky situation between two vehicles, but it could be with a great set of vehicles. So in this condition, we need to take into account the communication between vehicles in order to arm the other vehicle and the infrastructure, and then to propose some adapted strategy to minimize the number of collision. So about this four domain, you can see the different type of researches we address in UGE. So for instance, about technologies and system. So we develop automated and autonomous vehicle. So from now 25 years in the past lab, the Liebig, and now in PICS-L lab, we developed at least 10 prototypes. So last one is Zoe Reno with the full architecture embedded in order to have a level 3 and 4 of automation. We address also the sensor deployment and sensor data processing and the environment perception. We have also path planning and cooperative development. We have some issue about operating safety, energy management, and from infrastructure, we have also to manage communication in order to not only communication and also perception from the infrastructure in order to provide a point of view from the infrastructure to the different vehicles driving on a specific environment. It could be an urban environment, it could be also a motorway or a suburb environment. And so from infrastructure, we can see we developed a specific concept in UGE called Air 5G. It is the award of 5th generation. And so I said we work on the PDI, physical and digital infrastructure, with how to provide a set of technologies and also processes allowing to provide from the infrastructure additional information allowing for a nego vehicle to extend its perception and to react properly to a distant risk situation. So we have also the handle of road sign and road marking with development of new road sign, road marking, and new material for road sign, allowing to feed automated vehicle and in order for the automated vehicle to have more information in order to react to a situation, not only with the embedded perception, but also with information coming from infrastructure. And so then after we have some development about mobility services. So it is the focus on a set of lab in UGE, for instance, Tchiya and Licit. We work on how to optimize traffic, or to propose some new mobility services with ride sharing, ride sourcing, and with the management of mixed traffic, and how to develop a new service of mass mobility as a service, and to also propose some infrastructure adaptation in order to improve the efficiency of a specific area in terms of traffic and in travel time. And so about human factor, we have a lot of studies focused on acceptability. We propose some cognitive model of human behavior. We have some studies about also the interaction between a human and the systems and the vehicles, and also about visibility and perception from the human point of view and not the sensor embedded in the vehicles and infrastructure. And last one is about HMI and how to provide efficient data and information to the driver in order to understand the situation and to react properly to a situation. So you can see it is a lot of different researches, and it is interesting because if we look at in the right part of its slide, we have the different domain addressed by CCAM association. It is a European association about connecting a cooperative automated mobility. And there it is similar. So we address also the issue of vehicle technologies. We have also the key enabling technologies. We have integration of automated vehicle in transportation system. We have the aspect of evaluation, validation, pre-certification of the new mobility means and embedded systems. And also with a higher level, we have societal aspects and user need. And you can see we have all these topics in our definition of road ecosystem. And so, of course, we are involved in CCAM association. We are a member of this association. So, in order to have an overview of the full system, so we have 4 domains, but about the different researches we have to address in order to develop service and a specific type of mobility. So we have to address 3 main parts. First one, I said, is about the user and society. Inside, we have to address economic viability of a system. We have, so it is a first study, and we have to think about the financial cost of a new transportation mean and new transportation system, new service. We have to address the maintenance aspect, the sustainability, the evolution of this system in time, the earth aspect, and how we can recycle, reconditioning, and repake the system developed for a specific service. About human and user, we study also accessibility, the usefulness, usability, the confidence and trust, and the earth aspect. And about regulation and policy, we have also to address traffic rules, the issue of protection of private information, and the issue of cyber security and earth rule. So it is really the societal aspect and human aspect. Then we define the mobility service in order to define, to develop, and to have the first proof of concept. We have to address 3 levels in the design process. First one is about opportunity. We develop a system with specific automated vehicle. So we will check if in the perfect environment, without disturbances, without strong interaction with the environment, if the system is efficient and usable. Then, if it is okay, we will address the second level about feasibility. And then the goal is to check if the system is working properly in the ODD defined for this service and for a specific automated vehicle. So it means we will take into account some adverse condition with rain, with fog, for instance, and we will check if the system react properly and with a level of security. And the last one is the minimum maintainability. It is the case we reach the border, the edge of ODD, or we are out of the ODD, defined for this vehicle. So in this condition, we have to propose some degraded operating in order to guarantee a minimum level of safety. So it means in some condition, if we have a very degraded situation, then we will activate some specific function allowing for the ego vehicle to reach the emergency lane on motorway or to exit the current road in order to park on a safe area with respect to the other road user, of course. And then if we can validate these three levels, this means we have a first proof of concept about a specific mobility service and a specific system. So it is a lot of issues, challenges to address. And of course, when you will develop new mobility means, and now is more and more electrical means, you have to think about the energy management and the energy providing for the new vehicles. So it means you have maybe to implement new technology, you have to address a smart grid, the topology of charging station and the disponibility and also the financial cost. And once you address all these aspects, so you develop the real system, and the real system mean you have a vehicle, a mobility mean, with a lot of embedded functionalities. You have the dedicated infrastructure, and you have the software part, allowing to process, to handle the data provided by the embedded sensors and also by the sensor on the infrastructure. So it means you have to manage a huge, now more and more, a huge quantity of data and information, and you have to prove that you will have reliable data, you have enough data. So it is about the quantity. You have accurate and reliable data and robust data. So it is the quality of the data. You have a full accessibility of the data, a full disponibility, and you are robust to cyber attacks. So you have to implement some mechanism allowing cyber security and data protection. So about intelligent system and software, we will see then after the different types of module, function, algorithm we have to develop in order to have a full system. So it means it is a lot of issues, a lot of aspects to address, and on the top of this slide, you can see the different researches addressed in the international lab we have with QT in Australia. And first one is about human factor. The second one is about perception, decision, action for CAV. The third one is about the infrastructure, and so the new smart road. And last one is about traffic management with CAV. And we can see, and we cover the full, almost the full aspect of the full design of automated system. So now about system and technology. So it is this part on the right part of this diagram. We need, in order to understand the situation, to collect data from sensor and to apply some processing, allowing to extract usable information like obstacle, like the ego vector state, like the road configuration, like the environment with the presence of degraded weather condition or adverse conditions. So in order to address all these aspects, we made and we were involved in a set of collaboration with industrial partner, but also in a large set of projects. There it is only a sub-part of projects, because in UGE we manage really a lot of projects. For instance, only from my point of view, only for me, I was involved in more than 50 projects during the past 25 years. So we are working on, for instance, classification of disturbers. We have now some method based AI allowing to detect in real time the presence of adverse weather condition like rain, like fog. And it is very useful in order to provide some weight allowing to reduce the impact of the processing of a specific sensor impacting by a specific weather condition. So it is a case on this on the bottom left. You can see an overview of the different disturbances we can have in the road environments. So we have 4 main class of disturbers. And for instance, we have the physical particle disturbers. It is the rain, the fog, dust, and cloud. And we can see only with this class, we will impact the operating of a set of embedded sensor, like the LiDAR, like the camera, like also GPS. And if we have some electromagnetic disturbers, we will impact also the radar. So it means when you have to develop a perception system, you need, it is mandatory to use a set of different technologies of sensor. You need to use a set of different technologies of sensor in order to be resilient and to be robust to the presence of specific disturbers. So it is a taxonomy very nice in order to understand all the different disturbances, interaction between environment, propagation channel, and the sensor, and to be active and passive sensors. So for the first one, we address this aspect of disturbers classification in Sensity. Sensity is a facility in Champs-sur-Marne, allowing to control the weather and to test specific condition and also sensors in a control chamber where we control the temperature, the level of humidity, and we can generate rain, we can generate fog also, and we have also the control of different light sources. Weather Safe is international project with a lot of labs and companies and also car manufacturers addressing the evaluation and validation of sensor in adverse and degraded conditions. And so ESI is a company working with us on the simulation of sensor and environment and ego vehicle in order to prototype, to test, and to evaluate ADAS and also automated mobility system and means. So we develop also a lot of methods for obstacle detection, tracking, identification, recognition. So I wrote the belief plot map, but it's not the last one. Now we are developing new AI-based approaches, and for instance, this year we developed a new tracking system based on AI. And so we have also a lot of different algorithms developed for detection, tracking, notification, recognition of road attributes with several strategies, either with only one camera or with a set of cameras, like a multi-camera strategy, and with also some bio-inspired approach, like a multi-agent approach. So it was developed with VDECOM. It is a French research institute dedicated to the mobility and energy management. Then we have also we are involved in a Cooperative project, the future project, dedicated to automated mobility. We develop a lot of methods about localization for the ego vehicle with single model approach, like UKF, EKF, and such a method, and with a multi-model approach, like an adapted IMM approach. It is adapted interacting multi-model approach. And we propose also some method with a bio-inspired method like OKPS. It is a mix between particle filter, swarm, and EKF. And we develop in a strong collaboration with Canada some cooperative approaches with, for instance, dynamic DGPS and cooperative map matching approaches. And with also VDECOM, we develop a mix between IMM and SLAM. The first proof of concept was developed in 2015, and we made a demonstration of this approach in Bordeaux for the ITS World 2015. And so we have a lot of methods and strategies allowing multiple sources and cooperative fusion of the different attributes and information coming from the actors, so the key components of the environment. And so we develop several operating safety and cybersecurity methods. So with Canada, but also with some other French organism. So on the right part, you can see there it is what we obtain with the belief plot map. So we have the capability to detect the different objects. There it is with the merging of data coming from LiDAR, camera, and radar. And we have the capability to generate the free navigable space. And it is a very useful method, allowing to take into account roadside infrastructure, but the extended roadside infrastructure with non-linear shapes. So it's very efficient. And on the right part there, it is the using of multi-camera system for road marking detection and tracking. And there it is interesting because in this method, we take the road marking as obstacle, and we will detect this obstacle, and we will apply a tracking of this obstacle, and we consider the ego vehicle as a static object, and we have the moving of the road marking around the ego vehicle, the static ego vehicle. So it means it's very easy and efficient to manage the lane changing with such an approach. So there, because now we develop more and more AI-based approaches. So you can see, so with Sio-Song, Ieng, we develop a taxonomy of what is AI. So you can see it's not only deep learning and machine learning, it is really a huge set of approaches either dedicated to operational researches or logic and reasoning. And of course, we have a part of our machine learning. And in UGE and with Sio-Song, we developed a lot of approaches with a great part of all these techniques, approaches of AI. So, for instance, we developed several ego localization approaches with bio-inspired method, and but association and for tracking. So we use also BF theory, and in order to manage conflict between the association, target track association in a tracking system. So we apply also some method based on ISTRC, Hungarian algorithm. Dijkstra algorithm is more about graph theory. And with Hungarian algorithm, we have an optimal system allowing to take the best decision at the end of a tracking system. And there is something with FACILITATOR. We propose a clustering system, very efficient for obstacle detection and recognition. And with machine learning, we develop also a lot of methods for clustering of data, classification, and for the generation of belief plot map. It was the same thing. For the regression, for road marking detection. So, but we have to keep in mind that AI is a very large domain, and it is not only machine learning. So there we develop a lot of different applications like hybrid AI. We try more and more to provide explainability on the different approaches we propose. And we have the uncertainty propagation and out of distribution detection in a smart relearning process. It was done with UBC and University of Victoria in Canada. And we are starting to study GAN and transformer approaches. It was done in Prisma, and we continue to work on it. We proposed during the two past years some fidelity score in order to have look like a stamp, a label on the quality of simulated data. So it's very useful if you want to use some simulated data set in a training process. And also about path planning and decision making, we propose a set of different studies and systems based on a set of rules. For instance, Copilot based on 3 different sets of rules: the human rules, system rules, traffic rules. So it is yet the system we are using in a lot of experiment in different European projects. And we have reference point learning. We work on active inference with a company called Octo. And we develop elastic band and also potential field approach in order to improve the first one based on rules. It was in order to manage emergency situation, and then with this approach we can allow to handle the situation out of the ODD, but with the constraint to keep a minimum of risk. So we have, I said, the detection of adverse and degrading weather condition. So it's based also on AI approaches, and it is interesting because the method we develop is usable not only for one technology of sensor, but a lot of different type of sensor, like camera, like LiDAR, like radar imaging, like infrared camera. And also with the University of Tongji, we developed an optimization of right sourcing services in a connected environment, and with also automated vehicles. So it was based on LSTM, but now we have new researches based on GRU, on transformer, and some other methods. And in order to react to a specific situation, which could provide a crash, so we have to assess the risk level in real time. So we develop a lot of different methods allowing to assess the risk level in the road situation. And now with Australia, we are working on the using of fMRI in order to generate a map, a brain map of the risk perception for a human. So with this map, we can see the different part of the brain lighted by the perception of a risky situation. And so it's very interesting because the generated map is really different than the map and the brain operating in a normal situation. So it's I think it's very innovative work, and it will be very efficient in the future. So on the right part, you can see some data sets we collected in the Versailles area, so in the city center of Versailles, in the suburb, and in the motorway, with application of some AI-based system, like there it was with YOLO V5 and YOLO P, and with detection of and recognition of object, and also detection of lane and free navigable space. So now, in order to extend the perception and in order to have the capability to react to a risky situation, we develop also a lot of cooperative systems and communication means. So it could be vehicle-to-vehicle system, but more and more we are developing a vehicle-to-infrastructure communication system and strategy, allowing to, in fact, manage the entrance of automated vehicle in a motorway. So when the ego vehicle, the automated vehicle, is driving on the ramp, how it could negotiate and manage its entrance on the motorway with the respect to the conventional car and the other road users. And it's the same thing if we have the ego vehicle on the main road, how to manage with efficiency the entrance of a conventional car on the motorway. And so in this condition, we develop a lot of strategies allowing to take into account not only all perception system and local dynamic perception map from each vehicle, but we have now a more clever mechanism allowing to dynamically share the group of vehicles on the motorway and to collect data from a set of vehicles surrounding an ego vehicle, and then only we call that a branch, all the main car on the cluster, the server, in fact, will have the capability to send data to the other cluster, and on a specific cluster, it is a dynamic clustering. Is a real-time and dynamic clustering, and in function of the current situation, you will the system will share the space with different dynamic cluster of vehicle, and there the white car represent the client associated to a server, and from this dynamic architecture called CBL, and we have extension CBLG with the gateways, so the roadside unit on the infrastructure. We have architecture allowing to process data in real time, but with high frequency, and it's really efficient. And what we did is also to develop a lot of concept about this PDI with, for instance, the using of ISAD and LOSAD in the PDI environment in order to generate, for instance, a label given the level of accessibility or readiness of the infrastructure for the deployment of CAV. And we are working also on the new generation of HDMAP and of digital twin, digital shadow, digital model, in order to feed our simulation environment, and then in order to have a capability to prototype, to test, to evaluate our new generation of application services and systems in degraded conditions and a specific environment before to implement in our real prototype and to test this application, this new method on either control environment or in open area. But it is the same thing. we made all these different works and researches in a lot of projects and collaborations. So there you have a full overview of what is possible to develop with a PDI. And for instance, there it is the result obtained during the Horizon Europe Augmented CCAM project. It is a project in progress. And in this project, we developed a lot of different systems for two specific use cases. One about the roadwork in the field situation, how to avoid with high level of safety roadwork area. And the other one is about the management of insertion of CRV on the motorway. So we have the real vehicle with the embedded architecture. We tested the different strategy, method, approaches in the satellite test track, and also in the real condition in south of Bordeaux on the A63 motorway. And we made the same thing in simulation with the simulation of environment from the ego vehicle point of view, from the infrastructure, and with the same real application and with the real communication equipment. It's very efficient and very interesting. And there you can see it is in the real condition in the satellite test track. We have the generation of CPM, and so we receive CPM messages with an OBU embedded in the ego vehicle, and we build an extended map from this information. So from the infrastructure and from the embedded perception in order to generate an extended dynamic perception map, allowing for the copilot to drive by itself. So there it is the architecture we developed with their two computers, one for the ego vehicle processing and the other one from infrastructure with the using of a real onboard unit, real road sign unit, and we have the full communication with synchronization, and so it is something in real condition and in simulation. So there it means we have here a digital shadow, a real digital shadow architecture. So about decision making and path planning, we developed, in fact, 4 types of model. First one is the one based on the set of rules. We can have a generation of trajectories, a set of trajectories, minimizing a set of costs. Among costs, we have of course, the risk level. We consider the ghost concept, so we generate virtual obstacle in order to feed some strategies allowing to the ego vehicle to apply either light changing or to reduce the speed, or to act on the speed profile. So about the second type of model is a generic multimodal model developed in the PhD thesis of Jérémy Leroy. So it is this one. So we generate a lot of different trajectories with there we use a specific risk indicator called REMU. It is a multidimensional under constraint, under uncertainty risk estimator. And so the goal was to manage the traffic, the motorway traffic with inside a set of automated cars, not only one, but several automated cars, and with interaction with the other conventional cars. And the third model was developed in Lyon by the colleagues in the Lescott lab. So it is a cognitive model based on the operating of the human brain, and with inside some mechanism going to take into account the propagation of information, but also the short-term memory, the long-term memory, and the deformation and the loss of information we could have with the real human brain. So it's very interesting. It's very efficient in order to test some behavior inside a traffic with very realistic operating and very realistic feedback. And the last one under development was with the Octo company. It was based on active inference learning. So it is a method with a specific data modeling and with the last researches made in neuroscience. But the results are not so interesting, and so now we focus mainly on the two first aspect. And you can see what we have to address in order to develop decision-making and path planning algorithm. So you can see we have the embedded system with the using of embedded information sources, the different sensors, with the development of perception maps, local and with communication global, extended perception map. We have to address interpretation, anticipation, risk assessment, and the detection of unexpected events in order to generate a set of trajectories to also identify the best maneuver to apply to the car and to take into account a set of constraints and reward also for at the end to generate the different orders and action to apply to the car. And more we have to take into account the human in the loop because with level 3 of automation, we have interaction with the driver and we have to take into account the driver in the loop. And for each part, more and more we have to use AI-based system. And we have to apply training stages, and we have to handle and to generate a huge quantity of data sets in order to cover ODD and a large space of possible situation, adverse and degraded situations. And so there it is a screenshot of the copilot we apply in the Zoe Reno, and there it is the similar application in virtual environment. And at the end, in order to control the car, we applied action matrix with, for the meaning of this action matrix, is in the center, we stay in the ego lane and with the same speed. And if we are on the bottom one, center bottom one, so it means we will stay in the same lane, but with acceleration, then with deceleration. On the left part, it is we will apply lane changing with acceleration, with same speed, and with braking. And on the other one, it is we go on the right lane with acceleration, same speed. So we can see there, the only possible solution is to stay, the best one is to stay in the ego lane with the same speed, because you can see on the left one, we have an obstacle, so we can apply lane changing. And on the right part, we have no lane, so it is not possible to apply lane changing. About infrastructure, there it is the overview of what we call fifth generation of road. So first generation were the tracks. Second one, the road with pavement. Third one, the road with asphalt. Fourth one, the motorway. And now we have the new one, the smart road with the management of energy, with the generation of new information, and with smart infrastructure. You have also there a set of projects we ever managed or where we were involved. And there it is a different concept we handle in order to develop this new type of infrastructure, and in order to know if we have the communication capabilities, or also the level of data of HD map and information provided by infrastructure in order to support the automated vehicle and mobility. And with all this information, we have a fitting between the level of automation provided by SAE, so with level 3, 4, 5 for automation, and we have the same type of level coming from infrastructure, and so we call that smart road classification levels, and in function of the level of connectivity and digital infrastructure and physical and digital infrastructure. So we will have either the capability to have autonomous infrastructure where we can apply level 5 of automation, and in some situation we will have to adapt the level of automation of the vehicle, because we have not enough services and connectivity equipment to feed the copilot and the automated car. And in order to develop all this method and to test them in a lot of situations, so of course we have a simulation environment, but we have also a lot of different prototypes. So there it was a past one, an old one called Carla. There it is a prototype. It was a prototype dedicated to perception. And we have several simulation platforms, and now we develop this one. It is an Impact 3D platform with, in same time, the real Zorevino equipped with embedded architecture, with sensor, with the perception, the copilot, and the control of actuators. We have the same thing in a simulation platform with a 60 degree of freedom motion platform, and with immersive system with 240 degrees of field of view. And the goal is to have interconnection between this platform and the real car on the test track, and to have the 3D model of the real test track in this environment, and to work with both in same time. So it means the real car will get information coming from simulation, and the ego vehicle will see the virtual vehicle and the virtual ego vehicle, and from the virtual ego vehicle we will see the real car in the simulation, and to have both in the same time. And we have also some traffic generator like Simuvia developed in Lyon, and we develop interconnection between this traffic generator, Simuvia, and Civic, the platform allowing to simulate sensor, vehicle, environment, and application in order to have a real full system. So you can see here the different facilities and also data sets and also digital model we have in order to feed our researches. For digital, so I wrote digital twin, but it is digital model. We have a Paris block, so it is a Paris quarter between the train station called Gare de Lyon, Bercy, and Austerlitz train station. And we have the satellite test track, the Bougainville main road. It is close to Nantes. Transpolis test track. We have the full 3D model of Transpolis test track. And the motorway, A63 in Bordeaux. And we have this moment a 3D model on the Liposte area, the interchange with a couple of kilometers around this interchange area.
Dominique,
Yep.
thank you for the detailed and comprehensive presentation. We have 10 minutes left, and
Yep.
we have one question. So can we move to ask the question, and can you answer it?
Yep. So I can see the first one. Do you study the road safety issues in regard to the two-wheel vehicle? Yes, of course. About e-bikes, e-scooters, and pedestrian. These different researches are managed by several labs in UGE, mainly in Satori. For instance, l'APA lab. It is a lab mainly focused on human factor and addressing this aspect, e-bike, e-scooter, and pedestrian. It is a case, so from the human point of view. And it is a case also with the Tchiya lab, where there are some more technical studies and traffic studies involving e-bikes, e-scooters, and pedestrian. Yeah, I confirm. We have a lot of research here.
Dominique, and also in our lab with
yeah, we have a simulator. Bicycle simulator. Yeah, in Champs-Élysées.
yes.
Mm.
But it is not really our topic, research topic from Dominique and I.
Yeah. So yeah, I display it is a different digital model we have in order to feed our simulation platform. And so, for instance, this one is Paris. And the goal there is to test some specific application involving e-scooters, bicycle, pedestrian, buses, taxi. And there we have the realistic 3D model of Paris area, this Paris area, with the same furnitures, the same traffic sign, traffic line, everything looks like in the real condition. It is the same thing for this part. It is in north of Lyon. It is the Transpolis test track, and we have the full modeling of this part.
Thank you very much. It was very
You're welcome.
and detailed. Thank you.
I think it was a lot of information for this reason. With the presentation, so the PDF version, the different participants to this webinar could check inside maybe some specific researches or aspect which could be interesting for them.
Yeah, I'm sure that they will contact you.
Okay.
Great. Thanks.
Thank you very much.
Thank you.
Thanks.
Bye-bye.
Bye-bye.